We have 2 talks today, and then 2 more on Thursday. And on Friday at noon, we have our planning meeting. This webinar, as well as Thursday's webinar and the Friday planning meeting, are part of the Volcanic Systems Modeling Workshop for the Modeling Collaboratory for Subduction Zone Science. Sorry, I'm on the wrong slide. Which is part of the SC4D initiative. Today's speakers will be Philipp Ruprecht and Mark Ghiorso, and then Thursday, Emily Hooft and Christian Huber. I'd like to draw your attention to the fact that we do have another series of webinars and the planning meeting in March and then in May. All this information is available on our website. The link is shown here at the top of the page. Since you're all here, you've all visited this website. This is just a screenshot from the top part of the website. I wanted to draw your attention to the links and documents here. Specifically, at the bottom here of the screenshot is the report for this workshop. This is work in progress, and over the course of the next meetings, we hope that it will advance, particularly through your participation in the planning meetings. If you cannot participate in the planning meetings, or if you just have some comment, feedback, there is this asynchronous feedback form. It's a Google form where you can ask a question, make a suggestion. You can write pages in there if you would like to see something added to the report, have suggestions. Please feel free to use it. And of course, please come to the planning meetings. If you would like to engage beyond that in terms of this document and this initiative here, please send an email to Kyle and I, and we are happy to engage with you. With that being said, I'll give it to Kyle Anderson, who will introduce today's speakers.
So our first speaker today is Philipp Ruprecht. Philipp earned his PhD in geological sciences from the University of Washington, where he examined the length and timescales of magma mixing. He was a postdoc at Lamont Doherty before joining the faculty there in 2012. And since April 2016, he's been an assistant professor in the Department of Geological Sciences and Engineering at the University of Nevada, Reno. Philipp combines fieldwork with petrologic and geochemical studies in volcanic areas to understand magmatic systems and provide insights into volcanic hazards and forecasting. He's worked throughout the world, but most extensively in the Andes. Philipp's talk today is called "We Ask the Crystal Answers: Constraining Magma Storage Systems from the Crystal Record." Philipp?
And before Philipp gets started, I would just briefly like to interject. After each talk, there will be time to address questions. So please use your Q&A feature on your Zoom application to enter those questions, and we will go through them in sequence after each talk. Thank you.
All right, thanks Helge, thanks Kyle for the introduction. Yeah, and thanks for allowing me to share some of my thoughts in this workshop with you guys. Let me just first share my screen. Give me a feedback if you see it, please.
Looks good.
All right. Yeah, so thanks again. What I would like to do today is look at the crystal perspective of magmatic systems. Mostly still, of course, from the view of natural systems and the rock record itself. I think overall we want to kind of tie it back to modeling, but what Tom and George already presented on the maybe more plutonic record, I want to focus today primarily more on the volcanic record. What you see here is a BSE image from Puyehwek Korankauye from my student Heather Winslow, and it highlights, of course, the amount of detail we can glean already just by looking at this picture in terms of the textual intricacies, as well as the crystal record within an individual crystal in terms of zoning. And so I want to focus on the magma storage system. Of course, this is somewhat linked to the architecture discussions that we had last month, and ultimately leads also into some of the transport discussions that relate to eruption dynamics that will follow next month. But my focus will be on the storage today. And so let me start out first with thinking, showing you this this cartoon that many, probably all of you have seen over the last few years now, that ultimately raises a few questions that I want to bring up front that are in relation to modeling, which is, I guess, which I think is the focus that we want to kind of keep in mind. Where can petrology help? Where can petrology ultimately provide some important insight is really understanding what we want to model, what are the boundary conditions, how well do we know these, and how well do we need to know these, right? Those are some of the questions that modelers need to know, and we as petrologists have the ability to share that information with them. Once we have the view of the architecture of a system in place, like the one, this transcrustal system you see on the right, we have to ask ourselves, can we get away with a single reservoir? Do we need multiple storage regions? And within these storage regions, what is their physical extent? Are they connected in some form, right? And as you can see already with those sketches, the complexity is large, and we have little access to those deeper zones. So we have to look at the rock record as one way to get to recover some of that complexity. And so we need, the more complex the system is, the more data we have to have. And I think this is ultimately a take-home message, right? That we should embrace the crystal record and large numbers of observations that ultimately give us a much greater detail and much more richness of what happens at depth. If we understand the system, we can then ask questions of how actually the system responds on times and length scales of maybe the entire system or of the subsystem, right? Those are some of the major underlying questions we want to address. Especially in volcanic systems, and this is where Erupt and the SC4D have really championing this, is really the question, how is the system leading up to eruption? What is the state prior to the eruption? And so understanding the magma storage region as it is moving towards that eruption is of key interest. Of course, if we look at the long term as well, we want to understand if a system is, how it evolves over time. And that is often taken from the plutonic record. Once we have these things in place, the simple way we often still go about it is that we try to explain a system primarily with a single set of intensive parameters: temperature, composition, crystallinity. And while that is, of course, from thermodynamics, a good starting point, I think we as a community are moving way beyond this and try to understand how much variation in space and time actually exists. And that's where the petrology perspective can really help, and the crystal records really can help deconvolve those kind of complexities to then gain more information about the components, the actual processes, and their respective time and length scales. When I think of crystal records, and many of you probably have heard me say this, I think of it as crystal exit interviews, just like a stadium that has a lot of participants looking at events that occur in, let's say, on the pitch. And I apologize to any Brazilian participant here. This is, of course, an event that really had very different experiences in the stadium, whether you were on the pitch, whether you were in the front rows or in the upper stands. The kinds of experiences and the kinds of records you took with it are quite different. And the same is true for the crystals, what kind of crystal they are and where they are in the system. So how close they are to the action. And so if we want to understand what happens, what had happened in the stadium, for example, we could ask just simply what was the score, and we can maybe just have one interview and we get the answer. Maybe we need 2 or 3 to confirm it, but that's the end. But of course, we want to answer a lot more complex questions. Who scored in which minute? Was there an offside situation? What should Brazil have done differently? What did they make a mistake here in this goal? Right? Those are questions that if you ask more people, you get a very large variety of answers. And ultimately, you understand much better how that system actually, or how these events unfolded towards, for example, a goal. And in our case, an eruption, for example. And so that's really where the crystal record is strong and helpful, right? Each crystal has its own vantage point. The same event is recorded in some slightly different ways. And that is contrasted compared to the whole rock or melt record that is usually integrated over many events and many records. And we have a much harder time to really understand single episodes of change. One could, of course, how many interviews do we need to take to really capture the full diversity of the system? And of course, one could resign in despair and say, like, well, given what George was telling us about thousands and hundreds, hundred thousands and millions of crystals and even more, that ultimately make up a magma system as it is mixing, we will never capture that full complexity. And I think that we shouldn't resign in this way, because of course we can look at this in the context of populations, where populations of crystals have shared histories. Even though they are not completely the same, they do generally are sharing similar information. And if we do embrace this richness of information that is in the crystals, then we can really make some major progress in terms of the understanding of magmatic systems. And don't get me wrong, we are already doing a lot of this, but I think this is just the beginning, and there's much more we can do. One nice image, BSE image, that really highlights the complexity we are dealing with in magmatic systems is this image that recently was published in Fidel Costa's annual reviews article from Mayan, and Dawn Ruth was so nice to share it with me as well, to basically highlight the complexity we see in the crystal record. Right, on the right-hand side, this is a BSE image for the non-petrologist. So it shows plagioclase in blue, pyroxene in yellow, and then you have glass or matrix kind of scattered around with black vesicles. And if you just focus on the plagioclase crystal, the blues really show zoning that is usually linked to processes like recharge, heating, volatiles, changes in volatiles, and so on. And what you can see is that there is a huge amount of basically no crystal is alike. Every crystal has its own story with rather different variables that are recorded. And that's even true for simpler crystals like pyroxene, where you have some that have quite abundant inclusions like this B, and others that are more like simple like C or A. So this is ultimately the kind of rock record we are dealing with, and none of these crystals end up being put necessarily in a happy place. Just like if you look back at the soccer game I showed you, some of these people on the pitch were happy, others were not. So the same thing is true with these crystals as they are experiencing magma recharge and mixing in a storage system, right? So the question really arises, how useful is equilibrium, or is everything at disequilibrium? And to just be clear from the get-go, of course, equilibrium is a very useful concept in magmatic systems, and Mark will probably talk a lot more about it in a little while. But if we especially look at volcanic systems, they are disrupted throughout their lifetime. They are open systems where mass and heat is delivered episodically. Changes in T, so temperature and composition, is basically a constant or quasi-constant problem for these crystals that they have to react to. It's not just simply sitting in a magma chamber. Of course, as the magmas ascend within a crustal package, they immediately are moved out of an equilibrium condition. The changes in pressure lead to changes in solubility of volatiles. And so you may have crystallization, you may have latent heat release, and therefore changes in temperature. The crystals have to respond to those and rarely get back to a total happy equilibrium. And lastly, simply even as a magma convects, if it is zoned, you may experience the same kind of complexities. So equilibrium is a good starting point, but the crystals, of course, being commonly in disequilibrium, this is actually what helps us to learn something about the dynamic changes in the system as the crystal responds by nucleation, growth, dissolution, and what we use a lot, of course, is diffusion, and then also some kind of replacement reaction. And so in the end, where I think the petrology has really made some great strides in the last few years is that the crystal records now are used routinely to track these dynamic changes, at least to first order, and that we can link those to other signals, whether it's deformation, gas chemistry, geophysics, especially in the context of eruption forecasting and so on. So let me go a little bit deeper into some of the things we've learned from diffusion modeling. And I'm going back to one of the earliest papers from Georg Selmer 20 years ago, just to highlight for the people that are not petrologists, again, how does this work? This is from Santorini or Nea Kameni, a plagioclase crystal of a certain anorthite content crystallized, and is as it is crystallizing, it also incorporates, for example, strontium, and we can see the strontium measurements over here. We can make some assumptions of what is was the initial condition of that strontium content. Maybe it was this is what the paper suggested at the time. And you can also estimate of what the actual equilibrium condition should be for that strontium, which is this line over here. And you can see that the compositions are moving towards such an equilibrium, right? And we, of course, the community at large, as a whole, has advanced from these early studies and refined this in much greater detail. That's just the general concept, right? The crystals are placed into an environment where they are out of equilibrium, and diffusively they equilibrate. And because of this diffusion process, there is a time scale associated with it, and we can understand, for example, how long crystals resided in a new magma. These early studies, as they were kind of pioneering this, were usually done with a small number of crystals, maybe less than 10. And that, while that of course was really revealing and how this could be used, the questions remained whether that is at all representative, and whether they capture the entire variability of a system. And so coming back to our analogy of the soccer game and whether you understand the full complexity of the system, you just have to make more interviews. You have to ask more questions to ultimately really capture the nuances of the magmatic system. And that is the same case for volcanic systems. And we as a community have embraced that. These are a few studies from Etna, Kizapu, and Irazu from my own work, but also Shishalden from Dan Rasmussen, showing basically typically some kind of population diagrams, frequency diagrams of the crystal cargo that an eruption has. And you can see in terms of the numbers of observations that were made, these typically are in the hundreds and sometimes in the thousands, right? And you can also see, or you can recognize that by taking that many measurements, some of these maybe smaller minor peaks actually emerge and become meaningful, right? And so that ultimately gives us an ability to learn a lot more about the complexities of the magmatic systems that with just a few crystals would be lost. I will come back to the Etna stuff from Mar and Carl, because I think it's a really nice way to think about this in the context of modeling. But once we have a large number of crystals that we analyzed, and we really, we're capturing now 1,000 crystals compared to, again, millions or billions of crystals in a real system. But that is a subset that if you think of the vaccination plans we had, right? There were 30,000 people tested once people figured out this is safe, right? And they could ultimately vaccinate billions of people. So thousands of people of crystals is ultimately a reasonable number to capture a certain somewhat of the full response of the system. And then once we have that, we can learn something about how this magma system was assembled, what different components are contributed, what was it like in the past, referenced or kept in place through the core record of crystals, and how did the system change, potentially recorded in rim compositions. We can really understand the relative importance of different components, and these smaller components can be only then identified in a small in the system. Why should we care about these different components or contributions? Well, ultimately, I think it's, again, thinking of it from a modeling perspective, they do provide important insight from natural systems on the volume proportions of different components. And then that ultimately leads to an understanding of energy and mass contributions for any kind of modeling, if it's a fluid dynamics model, for example. They help us to understand really how the system was disrupted and how much hot versus cold magma is present, and whether it is equally distributed in a deposit or whether it is actually skewed in some form, which then tells us how efficient mixing, for example, has been, right? And all these kind of tie back to any kind of numerical effort that we have when we want to understand dynamics of magmatic systems. So let me come back to Malen's work on Etna. I think this is probably can't be recreated at every volcano, but it is a nice, it is a diagram that I feel like for us in a workshop like this provides a marker to see where we want to go or what we can do with this kind of data. And so this is basically, she did a very careful analysis of multiple eruptions. You can see a total of 8 eruptions from Etna, and looking at the olivine crystals through these eruptions. And what she recognized was that there was populations that kind of recur, and that these families have systematic relationships to each other. Right, that there is a hierarchy in this system that ultimately has to be linked or related to the architecture and the storage system at depth. Only with this kind of information can we ask questions of whether that system was basically behaving the same throughout an episode of unrest or 10, 20 years of activity, or whether how this system changed over time. At a level that ultimately, I think, makes use of the data to the point where we can link it in much greater richness to other data sets like deformation and degassing and so on. Moreover, she was looking also in detail of how these connections actually, what kind of connections exist, right? And that also gives us a sense of how the the system itself is connected, right? Which kind of olivine crystals are linked to overgrowth zones of certain composition and so on, that then highlight what is the dominant mode of this system being interacting and which ones are maybe more isolated systems. The next thing that could be asked is, yeah, if we have these different behaviors, can we tie this to seismicity? Can we tie this to gas chemistry and deformation? And then ultimately actually consider some integrated model approaches that Matt Pritchard was talking about last month, to where even petrology can really be fully integrated in such an effort. But as you can see, right, there is a large number of observations that are needed. How many crystals do we need? Well, this is, again, a question of the complexity of the system and what kind of questions we want to ask. Lilo Cheng from Singapore, working with Fidel Costa, has done some excellent work on exploring how populations ultimately are recorded in the rock record and kind of the complexities that they retain, and how that is linked to the dynamics of a system. So unfortunately, I don't have the time to show that work, but I did want to give a shout out to that work. It's an excellent work to ask, to look into, to understand how many crystals one really should look at. So this is the lead up towards eruptions and the short term, right? And related to unrest. But of course, the crystal record has also a long history that it can record. And a lot of that work has been coming from, especially from zircon studies, like this one that has been shown very frequently in the past from Lily Claiborne on Mount St. Helens, showing that this magmatic system was active for hundreds of thousands of years, with zircons being recycled and reintroduced into active eruptive stages. It allows us to understand how long the system was active, or at least could be remobilized. And of course, there is a lot more that could be said about this. Another shout out to Mary Reed's Bone lecture. She did a marvelous job, obviously, to present this kind of context in that lecture. So there is a lot more that can be said, but I'll just leave it at this. Nonetheless, we can also learn something from this long-term record, how it evolves over time, right? Is it, as Tom was saying, is the system cooling but growing? Those are questions that are coming back at this point as well. I would like to come back to the reawakening and ultimately the initiation of unrest, right? How does a system actually reawakens, and what is the state out of which it moves from? And those are the questions that we want to, I think, again, in the context of SZ4D, really address. I think an important aspect here is the transient nature of this. Can we really resolve the transient changes? Not just simply an average kind of time scale, but can we link it at the level that we can connect it to physical processes from other techniques through the times and length scales that we can obtain. And of course, what is the state of the system prior to eruption? Well, this is a long debate now. Well, not so long, but it definitely is an active debate whether magmas are stored really mostly in cold conditions or more at warm conditions. There's no reason for me right now to rehash this debate, but of course, I think we are all aware of this, that we are asking ourselves how the system ultimately is, what its long-term storage is, and how it is moved out of that long-term storage towards an eruption. So a lot of this information, just like, I mean, in the case of Kerry Cooper's and Adam Ken's work, this information was ultimately revealed from absolute age dating using uranum thorium and thorium radium, mineral separate data, and combining that with elemental diffusion modeling. So really exploiting this disequilibrium that I was talking about, and how these two data sets cannot be reconciled with a long, hot, or is hard to reconcile with a long, hot storage condition, or warm storage condition, right? But the important part is that we use diffusion modeling to extract that information. And so this is where I think the petrology obviously has made some major impact into the community, that we can use this disequilibrium and kinetic constraints, mostly through diffusion, to learn something about when did recharge and mixing occur prior to an eruption. How long did it take for remobilized components to be remobilized or then reside in the magma prior to an eruption? And then related to the more long-term question is, what are the thermal cycles that the system is actually coming through or going through over time? How long do different episodes last? And I think those are questions that we are still mostly struggling with, especially this last one. There's a nice new study though that I wanted to highlight real quick. Let me see what the timing is. Yep, I'm wrapping up. From Raud et al. 2021, which was looking this time at a very small number of crystals, but very uniform kinds of crystals from Tarapacá. On the right-hand side, you see a 1 centimeter scale bar of this sanidine crystal. So this is a multi-centimeter sanidine crystal in these dome eruptions from the Tarapacá volcano. And it has some really fascinating zoning, especially in barium. So the map on the right-hand side is what you see is the barium zoning associated with this growth. Barium partitions into sanidine as a function of temperature, with higher barium content being associated with higher temperatures. And so they have been trying to basically deconvolve this crystal record, in this case from a single crystal, to really look at the long-term thermal evolution of this crystal that, given its size, probably resided for a long time in this magmatic system. And so they did a very neat approach where they basically are looking at all these zones, overgrowth zones that happen, and look at basically sequentially go back in time and try to see how barium diffusion has been playing out, where the outer parts have not diffused as far, and the inner parts, of course, have diffused further out. And the key aspect that is really new here is that because you can actually learn something about the temperature itself from the barium content, you can look at this diffusion modeling, not isothermally, which is something we often do, but actually look at how temperature is changing and how that ultimately affects the diffusivity and the length scales that are coming out of it, right? And what they revealed in their study, which I think is a really fascinating work, is that this crystal potentially had tens of thousands, maybe 100,000 year history, that was dominated in the core by potentially a long-term cooling trend with intermittent small heating, and then an episode of rejuvenation, reactivation from a crystal mush on the order of a few thousand years prior to the eruption, and with that then kind of manifested itself with multiple episodes of mixing in the last few hundreds of years potentially. Right, so we have a way to really understand how the system slowly kind of comes out of its long sleep, and then returns to a more active phase and ultimately an eruption. Those are the kinds of data sets that are, of course, highly relevant to any kind of modeling exercise, especially thermal models, if you want to understand how these systems respond over thousands to tens of thousands of years. Of course, if we do diffusion, there are a few limitations, and I do want to kind of, word of caution that while we're trying to really link everything perfectly with other signals, whether it's numerical models or observations from the surface, these diffusion models ultimately have still a lot of uncertainties, and we need to continue to really demonstrate how well we can resolve things. We need to have excellent constraints on the diffusivities of certain elements. This is just an example from chromium and olivine from Mike Ullens that shows that depending on the silica activity, you may have a huge range, or large range at the very least, in how fast chromium diffuses. So we cannot blindly, obviously, apply this, and it's not simply a problem of temperature. It has a lot of other variables that we have to consider. And for some elements and or mineral element pairs, these kinds of models, diffusivity models, are well constrained, but others still require a lot more work. So a shout out for the experimental community to continue to do this work, which is really, really important to improve the timescales and information that we can get from the crystal record. And then lastly, unfortunately, crystals aren't as stagnant as we sometimes maybe see them later on in the rock record. They grow and they dissolve. And so we have to worry about moving boundary problems when we are looking at any kind of diffusion timescale. Can we account for this? Can we ultimately resolve this? For example, in the case of Hannah Shamler's and Christy Till's work, on the right-hand side, you can see strontium and barium diffusion in a sanidine as well. And these have very different diffusivities, but the same length scale of diffusion, which ultimately would lead to very discordant time information. And one way to explain this is that there is syn diffusion growth, for example, taking place. And in other cases, like olivine, life has unfortunately gotten a lot worse. And so we're working on this as a community, because these olivines are not necessarily growing as a concentric crystal from the inside out. So any diffusion, we have to ask ourselves whether concentric diffusion models always are valid. In many cases they are, but in the case that you see here on the left-hand side, this crystal really grows a frame and has huge melt pockets in the interior, especially this one in this case here, right? So if zoning emerges from this kind of growth, the kinds of diffusion models that one wants to take from this have to be in taking this into account. So my final thoughts, I think there is a lot of answers that are locked away in the crystal record. And we have been working on this for a few decades, but we are definitely on the verge of developing a much richer picture of the magmatic systems with respect to their assembly and their temporal evolution. And again, a shout out to Mahan Khan's work, which I think highlights the kind of power that the crystals have that we should embrace. We can then answer these very important questions that are associated with eruptions, magma transport, recharge and mixing, and many others. And this is information that is on top, of course, of the fundamental constraints we receive from equilibrium thermodynamics. And once we really merge this information, we can then tie the crystal records to the physical response to models through the information we have about crystallinity, viscosity, and changes in viscosity, changes in temperature, and potentially the role that volatiles play, as well as the different components that contribute to a magmatic system. So I really hope we are incorporating and embracing the large data sets, and we should learn from other communities in this sense. And I think the modeling collaborative is really important in this context, right? Other communities like the climate, atmospheric science community, or biology always deal with very complex systems, very large dynamic systems, and in the end have to also use a lot of information. Of course, there's differences to our systems, but I think we can, by taking full advantage of not just the populations, but also the functional form. What can we learn from the range of timescales we collect, the range of populations we collect? That ultimately has value for understanding the dynamics of the system. Thanks.
Great, nice job. So I just wanted to remind everyone to please use the Q&A feature to ask your questions. and you'll be unmuted during the discussion of your question. So we'll start first with a question from Paul Lundgren. Is there a balanced trade-off between number of crystals and number of different rock samples?
I mean, that is, you're raising another good point, right? I mean, whether we have captured the diversity even on let's say an eruption takes place, and how many samples are we grabbing from that eruption? I think that's the question you're asking, right? Is one sample sufficient, or do we need to capture many samples to really capture the full compositional diversity? And that in itself is, I think, I mean, that highlights the problem. We do need both. We need lots of information in a single sample, as well as large samples, large numbers of samples, at least for complex systems, right? I hope that answers the question. Of course, there are systems that are, you know, compositionally very similar and simple, where we can get away with probably a lot less observations. And I'm not trying to be, again, a devil's advocate for, oh, this is all a lost cause, as I said. I think it is actually we should embrace it and use it as a way to really learn a lot more about it than shy away from it.
Thank you for that, Philip. So this is not a question, but rather a comment from Michael Dongan. So Philip, thank you for a very well presented review. Total agreement with everything you have emphasized as fruitful research strategies.
Thanks.
Any other questions from the participants?
Okay, next question is from Chiara Montagna. Great talk. Do you think the non-homogeneity and or motion of crystals around the magmatic system could impair our interpretations of results? Could impair our interpretation of results from thermal and diffusion modeling alone?
No, I think the point is that we have to capture the thermal histories. I think that's exactly the point that we are not necessarily doing sufficiently, right? Most of the diffusion modeling is done isothermally, and the one that I showed from Taupaca is maybe an exception. And by being isothermal, maybe we can get away with it, but in most cases I would think when the system is in disequilibrium, there is also a thermal disequilibrium and potentially heterogeneity in the system, and we have to capture that. And this is not easy. I think this is the only way we can capture the state of the system and how much variation there is by looking at sufficiently large numbers of crystals, and then we can do diffusion modeling that potentially takes that into account.
All right. Next question is from Steffi Burchard. Sorry, I don't know how to pronounce your surname. But the question is, do you believe in the existence of persistent shallow magma reservoirs? They seem to become unfashionable, with the MASH model being most popular right now. But how do you explain mega crysts like the one from Taupaca?
Well, I mean, there is obviously evidence that shallow pockets of magma exist, right? I mean, whether it is melt inclusions that are degassed and they must have stored at shallow levels. There's no doubt about this. That, of course, is not necessarily the case for all systems. And then about the problem with Taupaca and being potentially in a really shallow system, I don't know if that's what you're meaning, but these crystals have been part of the magmatic system for potentially 100,000 years or longer. And if you're really at a very shallow level that is not constantly replenished, I mean, these systems would die out from a thermal perspective, is my view. So, and of course, the mush there is a good way to buffer this, right? Chris Huber and others have talked about this for a decade now, that the latent heat, that you really are sitting at a nice little thermal happy medium where this system can reside for a long time.
All right. We have a question from Patricia McQueen that says, do you think there is any bias in where these types of studies are conducted? Any types of systems that are oversampled? Any kinds of systems you'd like to have more data for? And how far do you think you can extrapolate the data you have on plumbing systems and residence times to other volcanic systems without this kind of analysis?
That's a point that I took out just for time. But I was, yeah, I mean, ultimately, of course, we don't want to create n number of unique problems, right? We need to find a way to categorize these magmatic systems in some form and learn from different types of volcanoes. And that is done in the community, that there is, of course, certain dome style eruptions, whether it's, Lassen and again, Tauapaka or others, right? We would compare those and we can definitely learn from one system something for the other.
All right, I think we do not have any more questions and we can now proceed. Oh, there's another one. Sorry, from Juliet Davis. Thanks very much for this talk. Do you have suggestions, perhaps based on your own experience, for how to approach collecting so much data? Is a survey approach versus starting with the targeted question the way you see forward with analyzing large populations of crystals? And or is there some way the petrology community can organize large quantities of in situ data that will be helpful going forward?
I mean, I think, yes, these studies have shown that we have, that we can generate large data sets. And I mean, one way that I think is really powerful is simply laser ablation ICP-MS into survey, right? There is so much, I mean, so much data one can generate, and depending on the kind of sample one deals with, one can make a mineral mount. That's what we did for Irazu, and analyzed 170 grains and got 6,000 data points or whatever. I think there is ways to collect that kind of information. Is it needed every time? No. I mean, again, I don't want to make us feel like that we have to now generate every time thousands of data points, but I do think we have to ask ourselves whether 10 is enough, right? I think that's the point, or whether 50 is enough, and whether we would be wise to collect, maybe an order of magnitude more.
All right, great. Thank you for the questions, and thank you, Philip, for the excellent talk. I think we have to move on at this point to our next speaker. For those of you who asked questions that we didn't get to, the speakers will see those, and they are recorded, so they may get back to you later with answers. Our next speaker is Mark Ghiorso. Mark earned his PhD from Berkeley for work in part on thermodynamic modeling of silicate melts, then taught for many years at the University of Washington and then the University of Chicago. In 2005, he left academia in order to co-found OFM Research, a nonprofit whose mission is to promote research on thermodynamic modeling properties of natural materials. Mark is currently vice president and senior research scientist at OFM, and he holds affiliate appointments at the University of Washington and Vanderbilt. I think Mark is probably most well known for creating MELTS, a software tool for thermodynamic modeling of phase equilibria in magmatic systems. He's now the lead investigator on an NSF project to develop Enki, a web-based portal for computational thermodynamics and fluid dynamics. Mark's talk today is Modeling Magma Storage, a Data Science Perspective. Mark?
Thank you very much. Let me share my screen. Thank you very much, Helga and Kyle, for inviting me to speak at this workshop. What I'd like to do today is talk a little bit about some questions that arise from a data science perspective, dealing with issues of magma storage and dealing with the whole notion of what a modeling collaboratory can do when aimed at addressing research problems in volcano science and particularly in petrological aspects of volcano science. Those of you that know me may be a little disappointed by what I'm going to talk about today. You would think that I would come and speak about equilibrium thermodynamics and modeling magmatic systems and how to do phase equilibria and so on and so forth. But what I'd like to do today is to talk a little bit about some of the science questions oriented around magma storage, but then answer those questions from a data science perspective. And I think this is really important. If indeed this workshop is aimed at trying to understand some of the issues and problems that will arise in developing a modeling collaboratory for addressing research problems in this field, it's important to know what models are and what models depend upon and what some of the important issues are in generating models and using them and maintaining them, getting access to them, and particularly publishing them. So I'd like to focus most of my talk on that. So if you're not particularly interested in that, now's the time to log off or go feed the cat. Let's start, though, with some of the modeling questions that do relate to magma storage, because I think putting these in context will help support some of the data science issues that I'll discuss. What are some of the things that we're interested in? In terms of magma storage, what are the temperature and pressures of the storage conditions? What phases are present and how much of each phase? That's largely a phase equilibrium issue. What's the volatile content of the magma? Specifically, is it undersaturated or does it have a free fluid phase? And that's important and goes directly towards the notion of eruptibility of a magma body. How does heat flow and crustal rigidity have an impact on the phase evolution and eruptibility? Now, this is an important issue. Most of the time when we model magma bodies or magma storage conditions, we tend to think of the magma body as being at a uniform temperature or a uniform pressure. We tend to think of the magma body as evolving in terms of its chemical evolution or its phase equilibrium evolution as an independent entity, but that certainly is not the case. The magma body sits in the crust. The crust has heat flow, which is withdrawing heat from the magma body, which controls the phase equilibrium evolution. And certainly the volume of crystallization and the volume of the magma body has to respond and engage with the rigidity of the crust. These are all important modeling issues, and these are some of the modeling questions that have to be addressed when we think about magma bodies in the crust. Is the system open and closed is another issue. And are the phase compositions, as Philipp just discussed, largely determined by reaction kinetics, by diffusion, by disequilibrium phenomena, and not the equilibrium state? These are all important science questions, and they all have to do with, and they all can be answered, or can be addressed at least, through some sort of modeling technique. But now, these science questions, or most of the ones that I just discussed, really do have a thermodynamic basis. Now, I know that Philipp has just discussed at length how at least the crystal cargo is largely influenced by disequilibrium phenomena, and I'm not going to argue with that. But from a modeling point of view, in order to understand the disequilibrium phenomena, we really have to know the equilibrium thermodynamic state, because it's the energetic deviation from the equilibrium state that drives the disequilibrium phenomena. And I think that's important to consider. When we talk about the kinds of models that we apply to magma storage condition, things like geothermometry and geobarometry and oxygen barometry, phase equilibria, and the kinetic questions, we're really always referencing the equilibrium state. And so we have to realize that if we want to construct models that describe this system, whether they be kinetic or largely kinetic, or whether they be largely equilibrium thermodynamic models, they always have to reference this equilibrium state. This is a really, really important issue. I mean, and it's important to understand from the context of how we develop a model. I mean, let's just take a simple example. Let's take the example of titanium rims on quartz crystals in high silica rhyolites. This has been an observation that's been exploited quite a bit in the last few years, and they can be interpreted in various ways. First of all, it is a disequilibrium phenomena. It is a kinetic phenomena that these rims occur. But is it because the temperature has increased in the magma body and therefore the partitioning of titanium to the quartz crystal has increased? Or is it because the quartz crystal is growing so fast that it simply is outrunning the diffusion event and growing at the same temperature as the rest of the magma body? Those issues can be addressed through models, but they require this equilibrium description of the activity of titania in the liquid, for example, in order to be fully addressed. So how do we, what are these models that we use that are thermodynamically rooted? And what tools do we need to actually develop these models? I think what's really important to understand is that these models do not just arise, right? I mean, we use them all the time. I'm sure that most people listening here have used at some point some thermodynamic model for describing phase equilibria in magmatic systems. But where do they come from? And the obvious answer is that, well, they come from experimental data. There are a set of experiments that have been done that allow calibration of that thermodynamic model, and then we use that model in order to address some issue that we're interested in. But what we have to think about in terms of a modeling collaboratory and in terms of using these models is that the process of model generation is complicated. And that's why I fully believe that models are first-class objects. I know there is a lot of discussion in the community that, well, a model really depends upon the underlying experimental data. And it's the experimental data that's important, and the model can be generated repeatedly and as an afterthought on top of the experimental data. That can't be farther from the truth. The model is a first-class object. There is as much research and attention and intellectual effort that goes into the development of a model as there is into the tremendous amount of effort made to actually gather the experimental data on which it's based. And so I think it's important in that context to recognize that models have to be treated in a way where their generation and documentation is viewed as just an important activity as the underlying data from which they were constructed. And I don't think we do that as a community. And I think one of the things that we can do, or we can advance through a modeling collaboratory which focuses on model generation and interaction, is to emphasize that concept. The other thing that's often stated is that experimental data are data, right? That are independent of any modeling exercise in and of themselves, and that cannot be further from the truth. There are no data in the sense of raw observations. There are always modeling layers between what you actually measure and what you actually use. No analytical data that's presented in the literature is independent of a model, because some model was used in order to actually reduce the observation to generate the analytical numbers. There are no data of any kind that we use to create thermodynamic models that haven't been processed through some sort of modeling filter. Heat capacities are model dependent, at least as they're represented in sort of functional form. And so that's an important exercise to understand too, that if we're using models and we're building models, we're making models from models. And if we're going to fully document the exercise of model generation and use, we need to fully understand what are fundamental observations and what are all the filters that have been used to go from the fundamental observations to the actual model that we actually use. So data are models. Now, having said all that, what I'd like to do is talk a little bit about some of the overarching goals of a model collaboratory that uses some of these thermodynamic models that are ultimately could be used in kind of a fluid dynamics context, or ultimately could be used in a kinetic context, but whatever. What are some of the goals for generating some of these models? And I think there are two major issues that have to be addressed. The first is model usability and reusability, and the second is model extensibility and maintainability. The second of these issues here is hardly ever addressed or hardly ever talked about in the literature, and I think it's probably one of the most important things that we can think about in terms of the use of models in this context. But first of all, what does model usability and reusability means? I think it's really important that any model should be easy to use. And I speak from experience here. If you create a model for understanding some aspect of the petrology or evolution of a magmatic system, if you and only you can use it, or you and only you have access to it, that's not very good. It's not very productive. It's true, you can publish a paper about it, but if the community can't use it, then it really doesn't make a lot of sense to do it. So a model should be easy to use and should be available, and as a consequence, it should be well documented. In the modern context, context of data science, what this means is that a model should be developed in a way which is commensurate and in concert with the paper that describes the underlying theory. And in modern data science, what's done is that the model is actually developed along with the complete description of it in a documentation format that is completely interactive. And in data science, the modern context for doing this is the Jupyter Notebook, Python-based models based on Jupyter Notebooks. But it doesn't have to be that way, but documentation should be important. The model should be robust and configurable. If a model is developed to solve some particular purpose, it really should be presented in a context where some different application or some related application can be solved using the same modeling software or modeling context. A model should be accessible. There's a number of petrologic models and a number of kinetic models, and a lot of the stuff that's published in the literature is not really accessible to the general user. And so what we're left with is a situation where model results are presented and people become intrigued with those modeling results. People try to use those results for some other application, and it may not be appropriate to do so. And that's simply because they cannot run the model themselves. So models should be accessible, which in the modern context means they should be runnable and replicable with a minimum amount of hardware, with a minimal amount of configuration, and in the best of all worlds, in the cloud. A model should be citable, and a model should be scalable. And most importantly, the software environment that the model lives in is transient. Then the model should be adaptable to the evolution of that environment. What do I mean by that? I've written a number of models that run in Microsoft Excel, for example. And what happens is that 2 years from now, Microsoft Excel will change. The underlying Visual Basic software, the underlying macros will have changed because Microsoft decided to change them, and now the model is no longer usable, it's no longer applicable. That kind of transient software environment is not suitable, and it's not appropriate for the kind of modeling that we should be promoting and doing. And so this lends to the concept or the notion that most models should be produced in open source software that is completely transparent and whose evolution can be tracked and maintained. What about model extensibility and maintainability? Models should have the capability of interconnectivity, and I think this is especially important in the concept of the model collaboratory. Models should not exist on their own and be completely incompatible with all other modeling software. I'll give you an example. This is an important example that I've worked on with my colleague Mark Spiegelman at Columbia University. Most thermodynamic modeling software, like MELTS, for example, is completely incompatible with most fluid dynamical software that models the dynamical evolution of a magmatic system. The inputs and outputs simply do not talk to each other. And that's ridiculous if you think about it. Then that's something that should be corrected. There should be an effort to make model development of various kinds interconnected, so that the inputs and outputs from one can be fed into the corresponding comparable model that does another kind of modeling exercise. We should have standardized application programming interfaces, inputs and outputs. It's important that models not be disassociated from their underlying data resources, and this is important in the concept of updating models and maintaining them. And then finally, models should be maintainable and updatable by a community of model users. And I think, again, this is an essential aspect of the model collaboratory. If as a community, we're going to promote the construction and use of models, then we should promote the construction and use of a community of model users. We should make the user community we should promote, or we should encourage the user community to actually maintain and update models. Now this may all sound just a little bit abstract, so I want to give you an example of something that I've been working on for the last 4 or 5 years now with a number of other users, including Mark Spiegelman and Aaron Wolf, and George Brigance, and Dmitry Stravinsky, and Everett Schock, which is the creation of this Enki thermodynamic modeling platform for the creation and execution of models. And I want to tell you a little bit about it because I want to give you a sense of what a model development environment can look like, particularly one which is directed at the sort of model creation that underlies thermodynamic models of magmatic systems. The Enki platform is available at enki-portal.org, and I urge you all to go take a look at that. The software depository for the Enki portal software is at gitlab.com. It's all open source, and I also urge you to take a look at some of the resources that are available there. But basically, the Enki platform is designed to build and maintain thermodynamic models using standard data resources. Right now, most of our development is being directed at the connection between the Enki modeling platform and the EarthChem data resources at Lamont Doherty laboratory. But the platform is designed to develop thermodynamic models using data resources and develop them within the concept of a uniform application programming interface, which facilitates model interconnectivity. One of the goals of the Enki platform was to create thermodynamic models that could directly integrate with fluid dynamical models. And the platform can actually allow you to develop thermodynamic models that compute physical properties of materials, which then can be directly input into fluid dynamical models that actually compute the consequences of interaction of those materials with fluids or magmatic liquids and so on and so forth. The Enki platform is Jupyter Notebook based and Python based, but the underlying source code and the underlying generated code is all in C and C++, so it's very, very fast. The Enki platform is browser based, and It runs in the cloud or it runs in Docker containers. And I think this is an important aspect of any sort of collection of models or model collaboratory or modeling platform which you work with. And that is that the underlying models have to be available to the largest number of people possible. And one way to do that is in the cloud through browser access. The other way to do that is to create a software environment which is self-contained as a Docker container and have that container runnable on any hardware platform, whether it be desktop, laptop, Windows, Mac OS, Linux, it doesn't really matter. The software should be available universally without extensive configuration. One aspect of the Enki environment, and I think an important aspect of any model creation environment, is that the modeling environment allowed directed model development rather than apps. I think one of the things that we suffer from in our community is that there's too much usage of apps. And this may sound rich coming from someone who has developed one of the apps that a large number of people use, which is Melts. Melts allows you to do one thing and with some configuration, but basically one thing, which is equilibrium crystallization. It doesn't allow you to go in and use the underlying thermodynamic models in creative ways which are not configurable from the app interface. That is a bad way to do model development. I say that in retrospect, having built a reputation on Melts, but it's a bad way to do it. And what we really should be doing is creating a modeling environment where theory can be translated into direct application without having to fight available software that just allows you to do one and only one thing. Probably the worst app I can think of at the moment is Excel. And I say that in the sense that Excel allows you to do a limited number of data analysis in a limited number of ways and constrains the way in which you can think about data analysis. That's what we want to get away from. And that's one of the things that the Enki environment is trying to create. The Enki software is community maintained, it's entirely open source, and it provides an important aspect, and it provides a natural publication workflow. Let me give you an example of one of the things that you can do in modeling using this environment. And I wanted to just show you a typical model development workflow for a thermodynamic model and give you an idea about some of the advantages that we have now through this application of sort of modern data science techniques. It used to be that when you were trying to develop a thermodynamic model, let's say it's a geothermometer or a geobarometer, some thermodynamic properties of some material. Let's say a recent application that I've just been working on that I've almost completed. Let's say we want to add zircon saturation to melts. That's something that I'm working on at the moment. How would we go about doing this? Well, in the past, what would have to be done is we would have to do some sort of theory, which would involve theoretically figuring out exactly how the thermodynamics of zirconium in silicate melt would be modeled, and then how that would relate to trying to understand zircon saturation in silicate melts. Once we had that theory worked out, then traditionally we would have to do quite a bit of calculus and algebra to figure out what the thermodynamic formulation actually looked like, and then do a fair amount of computer coding to actually code all that theory and form a model, which we could actually use then through calibration. Once we had the model calibrated, we'd probably have to go start over because we made a mistake the first time. We go through this cycle a few times, we do some more coding, and finally we would produce a new version of some piece of software that allow you to do zircon geothermometry or allow you to do zircon saturation state and silicate melts, or so on and so forth. This traditional model development path is one that takes a long time. It would take me, let's say, 6 months, 9 months to actually go through that path. It would take other people less familiar with the underlying thermodynamics perhaps longer. Maybe it's like a master's thesis kind of process. But the important thing is that's a rate limiting step, and it's also a deterrence to actually wanting to do that kind of model development. What modern data science allows us to do, and what the Enki platform allows us to do, is to bypass much of the tediousness of that process. So now with the Enki platform and with this current model development environment, we can devise theory and stipulate that theory using symbolic methods, symbolic calculus methods. And then from that automatically generate computer code that does all of the things necessary for thermodynamic analysis, for calibration, and for translation of calibration results into application. We still have to interact with this computer code. We still have to do the calibration, but the focus can be on the science rather than on the actual manipulation of the underlying manipulation. So I think that aspect of model development is important. And what that aspect of model development does is it democratizes the process of model development. You no longer have to be an expert in coding. You no longer have to have a great deal of time on your hands to actually go from theory to coding to calibration and back again and make these long, tedious circles. If the whole process of going from theory to application can be automated. And that's one of the things that I think we should strive for in creating a model collaboratory. The other thing that we need to worry quite a bit about, and I'm really quite serious about this, and I think little attention has been given to it, is how we publish models. And particularly how we publish models in a replicable and reproducible fashion. And I think without insulting too many people and without being too pedantic, I think I can say right now that the way in which we publish data and models currently is absolutely abysmal. And it's abysmal in the sense that it doesn't allow us to actually use any model that's published in a replicable, reproducible, and extensible way. Why is that? Because when we publish models, what we tend to do is publish results. We tend to publish papers that are static. We tend to run a model, let's say, extensively and produce some result and stick it out there in Nature or Science or wherever it is that will give us the best reputation. And it's completely unusable in the way we've published it. I know there are supplemental materials, there are extra information that we think will help others replicate the analysis. We think it will help others and actually use the or extend the analysis that we presented, but rarely is that the case. I've published many, many papers dealing with modeling in the petrological sciences, and I can tell you right now that not a single one of those papers contains enough information to actually replicate the analysis. That's my fault, that's the editor's fault, but that's the way it is. And it's because you never really are given the freedom to publish everything necessary to actually allow complete replication of the analysis and to allow you to extend that analysis to use those models in subsequent activities. Almost always the model has to be distributed separately, and there never then is a context between the development of the model and the actual model availability. The other thing that is never done is the actual calibration software, the actual process, the intellectual process of taking the model from data to final product is never sufficiently documented to allow someone else to actually reproduce that. We need to fix that. If we're really interested in encouraging the use of models in the petrological sciences, in the volcano world, then we really need to build a system where the entire process of model development, the process that goes from data to final model, can be completely replicated. And I think we need to change the way in which papers are produced, constructed, and published. And so on the right-hand side of this screen, I've described a little bit of the concept of the self-contained modeling paper. I call it here a Jupyter paper because I'm focused, or this particular application is focused on the publication of Jupyter notebooks. But the idea is to create to publish a complete modeling environment. And that is a complete self-executing software environment that allows you to go from the data through the complete analysis, through the production of a model, and then instantiate all that in a self-contained container and publish that container as the paper. That way, anyone can take that container and simply look at it to see what you've done, or instantiate it into the cloud and run all those notebooks, run all that software to actually replicate that model, figure out exactly what you did. And if someone is really, really interested, they can then take that software container and they can modify that container and perhaps produce a derivative product which is based on the actual model that you chose to publish. This notion of being able to take a data package and fully describe how that data package was manipulated to produce a model, and then allow someone to actually replicate and work with that model in real time is, I think, a notion that we have to try to advance. And I think this is the paper of the future, and this is certainly the way in which models should be published. With the Yankee environment, one can do this now, and I think the challenge for our community is going to be to find publishing resources that can accommodate the publication of fully dynamic modeling papers like this that are responsive to all the underlying data science issues. Okay, so what I want to end with are just a few thoughts for thinking about models in the context of a model collaboratory, and what we should think about in terms of how models should be developed and used and published. I think it's important, as I've mentioned, to focus on model interconnectivity. Models should not stand alone. Models are generally constructed to solve a particular problem, but there are a whole series of problems that are interconnected. And so we need to have results from one model feed into another, or for the results of one model to be acceptable to the model that you're working on. So there should be this focus on interconnectivity. And what that means, of course, is that there should be a standardization of the way in which we output information from models. There's no probably worse example of this than current thermodynamic models for various petrologic scenarios. The input and outputs to melts are completely different than the input and output to aqueous solution equilibrium packages like EQ3 and the deep earth water model, which are completely incompatible with thermodynamic models for metamorphic phase equilibria like thermocalc, which are completely incompatible with models for fluid dynamical evolution of these systems like aspect or like terra firma. That needs to be fixed. If we want to have a fully integrated modeling environment, we need to worry about how models interact with each other. We also should be promoting open source tools. I know that the community as a whole is in love with Excel, it's in love with Mathematica, it's in love with MATLAB, it's in love with a lot of proprietary software products, but those are not always available to everyone. And they change underneath you in ways that prevent models from having a longevity that we would like them to have. So if the community moves to open source tools, that can be mitigated. Also, along the same lines, community involvement in model production is important. And I speak from experience. One of the frustrations of being the person that that mainly led the development of melts is that you end up being the person that everybody goes to when melts needs to evolve, or when some sort of thermodynamic model needs to be added to the system. And that's a wonderful position to be in, and I'm not regretting being in that position, but that's not the way in which model development should take place. We should create model development environments that engage the community and cultivate a user base, and encourage the participation of the broadest range of people possible. And that has consequences. One of the consequences of that is that the more people that are engaged in model development, the more people learn about the underlying theory and best uses of the models that are created. We should make calibration tools and data sources available for model extension. And I think that goes hand in hand with this notion of community involvement of models. And I think it's incredibly important that we promote an environment that democratizes the access to models. And in that, one aspect of that is to discourage the use of proprietary software. But another aspect of that is to minimize the need for software installation. For years and years and years, I released versions of the MELT software that only ran on Macintosh systems. And that was not a good thing to do. And nowadays, fortunately, through the efforts of many of my colleagues, the MELT software is available on other systems, but there are still limitations to its use. And one still has to have a fairly sophisticated computer system to run some of that software. And that's not a good thing. We should be able to use models on our phones. We should be able to use models on our iPads. We should be able to use models on any sort of minimal computer connection equipment that we have. And in that sense, we should minimize the need for extensive software installation and resources, and try to have models accessible as broadly as possible. And for the most part, that means that we should try to encourage model development in the cloud. It's absolutely essential that we make models replicable and reproducible. And I don't think we should even allow the publication of models anymore unless replicability and reproducibility and extensibility is part of the publication process. Models should be published, and they should all have DOIs. And I think that one of the, and it's just as data nowadays are published with DOIs, I think models should be published with DOIs, and they should be citable. And even if the model is presented and published in a self-contained fashion in a container, it still should have its own DOI. And I think it's really important that everyone who participated in model development get credit. Oftentimes this is not the case. Oftentimes the the undergraduate who did the user interface for you, or the graduate student who wrote that little numerical package that wasn't essential to the theory or science development, gets left off or stuck in the acknowledgements of the final paper. And that's something that we need to fix. And finally, in terms of publication, supplemental documents are not adequate and should be discouraged. Data and model repositories should be the new paradigm for model distribution. So I thought I would end there. And I realized that I didn't really talk about science applications of equilibrium models or of petrological models. But I thought it would be more important to talk about this context of model development, since ultimately that was the purpose of the RCN forming talking about issues dealing with model collaboratories. Thank you very much.
Thank you very much, Mark. That was fantastic, and just what we needed for the purpose of these workshops in terms of discussing modeling and MCS. We do have the official ending time of the webinar was 1:30, but for those of you who are interested, there are a number of questions. We'll try to address some of them, and this webinar is being recorded, and we'll make it available on the website. So if some of you are curious about questions and answers, feel free to visit this at your leisure if you have to leave us. Give it to Grace and Kathleen.
Yeah, so from an anonymous attendee, so question is, if the way that we present model results in static is static and inappropriate, what would you suggest are best practices for doing this?
Well, I think that I think current publishing paradigm, right, necessitates that we, or the usual avenue for publication of these things is static. But I think if that is the only thing that's available to you, then I think it's really important that the underlying model be thoroughly documented and available. And what I mean by that is that not just the final product, but the actual mechanism that you went through in going from the original data to the final product. That those intermediate steps are often not documented anywhere, but if they were actually available. So in other words, if you had to put a supplemental document attached to your paper, that supplemental document should be a complete workflow from data to final product, so that somebody could actually go in and try to replicate that. So that's, I think, one way to address it.
Great. So a question from Robert Backhurst. Fascinating talk, thank you. Thoughts on increasing accessibility and understanding of models produced using paid-for software?
Yeah, it's a hard problem, isn't it? Because there's a lot of really good software that that you have to pay for, that you have to give a license to. And I like to use that too, but I have made a decision, and this is sort of a personal decision, that I will not publish any model that now relies upon proprietary software. And I realize that may not be an option to you. And if it isn't, well, then that's fine. That's the way it is. But the problem with that is that it really limits use. I mean, so as an example, I work at a not-for-profit institution. OFM Research has a grand total of 2 employees. We don't have an enormous research budget to buy software, so we don't. So I don't have access to Mathematica, for example, or MATLAB. I buy Excel, but only with great reluctance because I couldn't communicate with my colleagues if I didn't have it. There are all sorts of issues like this. So there's certain pieces of software that people develop and release that I can't use. Now, I can work around it, but you just have to realize that if you do have a model that is built on paid software, you are limiting the use. And I think what you really have to think about when you develop a model that's based on paid software is, who do you want to use the model? If you're developing a generic model that you would like to see used by you would like to see used internationally, or you would like to see used by a diverse group of users, or you would like to see used at the undergraduate level or the graduate level, where a department or an institution may not have the funds to buy the paid software on which that's based. You have to really think about whether that's your aim. If you're developing generic modeling, if you want to engage the community in model development, and you're starting with a piece of paid software for model development, that's just not going to work. So I think it's an intention. It's what you intend to use, or how you intend the model to be used. That has to underlie your decision whether or not to build it on something that is paid. But I have to tell you that in the modern data science environment, and by that I mean largely the modern Python, R, Julia, and all these open source language environments, there is nothing that you can't do with some public available Python package. So when you build something on paid software, give it a lot of thought as to whether with maybe a little bit more work, you could learn a little bit of Python and learn how to use a public source open Python package that might accomplish exactly the same thing.
Okay, so for the next question, another anonymous attendee, so he said, or she said, congratulations. I think you touched a really important point for future science. I just have a couple of questions. What program language are you using to build your modeling collaboration software? What could be modeled with this software? Magmatic systems, crystal mesh, or what else?
Yeah, that's a really good question. The programming interface, the modeling interface, which is largely accessible through Jupyter notebooks, is Python. But Python is not the language that most of the software is actually built in. Most of the software is built in C and C++ and Objective-C and higher level languages. And one of the things one of the decisions we made in designing the Enki environment was access should be simple. It should be uniform. So a common language and a common programming interface for all of the underlying thermodynamic packages and for all model development was adopted. And that common environment was Python and/or R, which are pretty much interchangeable. And they both run within these Jupyter notebook environments. But one of the important things is that when models are developed, like for example, when a new thermodynamic model is developed, its specification is done in a Jupyter notebook in Python, and its specification symbolically is done in Python and LaTeX. But then when the model is developed, the software automatically takes the Python specification and translates it into C or C++, and then compiles that and reintegrates it back into the model development environment so that it's fast and the computations can be done in as efficient a way as possible. Right now, we've used the Enki environment to give users access to all of the currently available thermodynamic modeling packages, including all of MELT's, all of the aqueous solution package of Helgeson and Woolery, all of Holland and Powell, Stixrud and Lithgow Bertoloni, and other thermodynamic packages like Helgeson and so on and so forth. So all of those are available, plus all of the ability to generate new thermodynamic models. The packages are designed, or the environment is designed in a way that allows you to come in and design whatever application you wish in a self-documented Jupyter notebook, so that if, for example, you wanted to make a geothermometer involving olivine liquid phase equilibria, you would open up a Jupyter notebook, you would instantiate the thermodynamic model for olivine that, let's say, comes from Meltz or Holland and Powell. You would instantiate a thermodynamic model for the liquid that could come from Holland and Powell or from Meltz. And then you would call on functions that for a given composition derive chemical potentials for those phases in those various models, and then you would combine the chemical potentials in such a way to construct a geothermometer and calculate equilibrium temperatures. So it allows you to design applications at a very, very basic level if you know the underlying theory behind the application you're trying to develop. It doesn't force you into a particular app paradigm. Does that answer the question?
I think so. From an anonymous attendee, though.
Yeah. Next question is from Antonina Calahorano. Thank you so much for the visionary talk. How would you deal with the issue that open source software like Python evolves very rapidly? For example, modules could not be compatible from version to version. Would it be enough to have an involved community, or would it be necessary to have some staff constantly updating the model?
That's a fantastic question. And that's a question that comes from someone who's deep into the open source community and understands some of the issues. That is a problem, and it's a moving target. There are all sorts of things that move underneath you in the open source world. Changes to Python are part of them, but changes to Python packages are probably larger than that. I think one of the things that you can do in terms of model development is to lock in various versions of packages that your model is dependent upon. And one of the wonderful things that can be done in the context of creating models that run in containerized software snapshots is that all of the software, and when I mean all of it, the operating system, the version of Python, the version of the Python packages, everything that your model depends, can be containerized and locked, so that your model then will always run in that container no matter how the software ecosystem is evolving around you. That's a wonderful thing as far as model replicability is concerned. It can be used forever in that context in the future. But as far as extensibility of the model, then you run into the problem with, okay, now if I want to change something, what about suppose I want to add a feature which is not supported then by the underlying software? Well, then you would have to do the port to a new platform or a new software environment. I think that's a burden that I'm willing to take on, and I think it's a burden that the community needs to sort of evolve to the point where they're willing to take on. But it does indeed require some small group of people to be in charge of to be sort of leaders of the user community that runs the modeling environment, or that maintains the modeling environment, because there still needs to be a level of expertise there that confronts issues of software changing underneath you. I think this is commonly the case in the physics community. It certainly is in the case of the data science community. It's commonly the case now, I think, in the geophysics community. I think our community needs to come to grips with the fact that there is this this burden of open source, which in my mind is fully compensated by the negative aspects of proprietary software, but it is an additional burden.
Thank you, Mark. I think in addition to what you've said, like containers can be used just so it can be, you know, stable to run this kind of models.
Right.
Yeah. And with that, that may be our last question. Helge, if
yeah, I think we should wrap it up. Again, those of you who have asked questions and that haven't been addressed, we're recording them and we'll pass them on to Mark. And if he has time, he will respond. But it's up to Mark. Thank you, everybody. Thank you, first and foremost, to the speakers. Please join us on Thursday for the second webinar. Speakers will be Emily Hooft and Christian Huber. And please also join us on Friday for the planning meeting, where we can continue this discussion. And I think a lot of these questions that are still up there could be discussed on Friday. And that's it. Thank you. Panelists, if you would like to join in a short debriefing, I send you an email with the Zoom link, but don't worry if not. Just Kyle and I will meet.
Thanks again, everyone.
thank you.